All right, well, good afternoon. It's a pleasure to be here and introduce our colloquium speaker, who is Professor Nicola Spaldin from ETH in Zurich. Actually, I have a few things to say about Nicola, but I think just to sum it up, I think she's a leading sort of theoretical and materials physicist and scientist, and renowned for many contributions to the field of magnetic materials, including sort of most prominently kind of major contributions to the dawn of multiferroics. And I kind of somewhat inspired by our conversation just now, I can't help to say I met her for the first time about 20-some years ago. Yes, I know. And it was over, it's part of a collaboration where we sort of found that bismuth ferrite, which has become, I think, since then the paradigm of a multiferroic, and really because of the subsequent work Nicola has done in that area, it came as part of a collaboration on this system that we did with Ramesh, one of our former colleague, and basically got to know her very well during that time and work with her and have been in touch ever since. So this is kind of a very nice personal thing for me to be able to host Nicola and give this colloquium. Just a few things about Nicola. She got her PhD at Berkeley, maybe almost some number of years ago, let's just put it that way. And then did a postdoc with Karen Rabe at Yale when Karen Rabe was at Yale. And then held a faculty position, full professorship at UC Santa Barbara before joining ETH. And as I mentioned, she basically has developed the theoretical underpinnings for multiferroics in that framework, and done a lot of foundational work on bismuth ferrite and other magnetic systems. And she's been widely recognized, and I'm not going to be able to read all of these awards, but there are many. The APS Magrotti Prize, the L'Oreal UNESCO Women in Science Award, the Swiss Science Prize Marcel Benoist, the EPS Europhysics Prize, the Hamburg Prize for Theoretical Physics, among others. She's a fellow of APS MRS in the Royal Society and a former foreign member of the NAE. And she's authored a textbook on magnetic materials, which I think is in its second edition. So she's currently a visiting Miller professor, and this is her second stint as a visiting Miller professor. Welcome back, Nicola. It's a delight to host you and look forward to your presentation.
Thanks. Does it make any difference? Oh, there we go. OK, now we've got it. This cusp in the magnetic susceptibility would have been very unexpected, because a cusp in a susceptibility tells you you've got a phase transition, and the thing that's ordering is the property that's associated with the susceptibility you're measuring. So in this case, we're measuring magnetic susceptibility. This is telling us that we have a magnetic order at some critical temperature. But the only kind of magnetic order that was known at the time was ferromagnetism. And manganese oxide was, of course, not a ferromagnet. So this was a discovery of a hidden order, an order that's there. There's some peak in susceptibility, but it's not amenable to being measured by techniques that were available at the time. And so that's what I'm going to mean when I say hidden order. It's not particularly exotic necessarily. It's some evidence for order in some measurement or some calculation, but there's no way of actually directly detecting it. So it's still hidden. OK, and of course now we know, in fact, very soon after that experiment was done, Nayel proposed that there was a phase transition to a magnetic order, which we now call antiferromagnetism, that the magnetic moments were ordered. These little arrows are representing the magnetic dipole moments. These would be spins in the case of manganese oxide. But there's no overall magnetization. There's an equal number of up magnetic moments as down magnetic moments. And so this explained how there could be a cusp in susceptibility, and also that there was no net magnetization to measure. And Néel went one step further than that. He showed theoretically that the form of the magnetic susceptibility is consistent with such an anti-ferromagnetic ordering. So he had an explanation, a theory that was consistent with what it was observed, but still, I'd say the order was still hidden. There was a kind of, it was post-dicted, if you like, by the development of this nice theory, but there was still not a direct measurement. Everything made sense, but there was no direct measurement of the anti-ferromagnetic order. So this took about another 20 years, and I'd say the first direct measurement came from neutron diffraction. And here I'm showing you the first data from 1950, something, 1954, I don't remember exactly. Sorry, I didn't put the date on. Of the neutron diffraction from manganese oxide above the ordering temperature, so when all of the manganeses are disordered, and below the ordering temperature when they're lined up in their anti-ferromagnetic state. And above the ordering temperature, you see the peaks in the neutron diffraction that correspond to the Bragg peaks that correspond to the crystallographic structure. The only order in the material above the magnetic ordering temperature is the ordering from the crystal structure, and these peaks are consistent with the known crystal structure of manganese oxide. But then below the magnetic ordering temperature, the symmetry is lowered because the manganese atoms become inequivalent. And we have additional peaks now. Of course, we still have the crystallographic peaks, but now there's additional peaks associated with the additional magnetic order, the additional symmetry lowering. And if one analyzes the details of which peaks are there, one can extract precisely what the magnetic order is. So I would say that after the 1950s, when we had neutron diffraction, antiferromagnetic order was no longer a hidden order. It could be really measured directly and quantified. And this was very important. So Néel received the Nobel Prize in 1970 for fundamental work and discoveries concerning antiferromagnetism. And for the development of neutron diffraction, Clifford Schull shared the Nobel Prize with Bertrand Brockhaus, who developed neutron spectroscopy in the mid-90s. But I'm a theoretician, so I can say this. This seems a bit unfair, I think, that the theorists in the 1970s and the experimentalists in the 25 years later. I think that's a bit, personally, I think it's a bit unfair because, I mean, building a neutron diffractometer is a really big deal. But anyway, that's how it was. So. Okay. Maybe some of you have read Néel's Nobel lecture. He made this beautiful statement in the 1970s. A large number of antiferromagnetic materials is now known. They were extremely interesting from the theoretical point of view, but do not seem to have any applications, which is, I think, a really nice example of the importance of fundamental research, because today antiferromagnets are hugely important from a physics point of view and technologically. And so I want to give you two examples, because I'm actually going to loop back to both of these later. The first, this is an image from the high magnetic field lab, or a cartoon, of the phase diagram of the cuprate superconductors, the high temperature superconductors. And so this is temperature as a function of doping of the number of carriers. And this is the superconducting dome that we're normally interested in. So I dope this many carriers, and I get superconductivity up to around 100 Kelvin. But look at this. Importantly, I start from an antiferromagnetic insulator. And this is believed to, this clearly has important implications for the development of superconductivity and for the richness of the whole phase diagram of exotic superconductors. So from a basic physics point of view, antiferromagnets are not just kind of inert, like not very magnetic things. They're extremely important because of the physics they then convey onto kind of their neighboring compounds. Then an example I want to give you of technological importance of antiferromagnets is in magnetic sensors. Okay, so this is an image from Jay Storr from SLAC, and this is just a magnetic read head, a magnetic storage device, and the component in a magnetic storage device that senses the data bits, that senses the magnetic field, I want to just talk you through the structure, is what's called a spin valve. And it works by having two ferromagnetic layers, one which is stuck, the reference layer, and one which can change its ferromagnetic orientation in order to sense the field, right? And what happens is when The sensor is parallel to the reference layer. There's a low resistivity. There's not much scattering of the electrons because they're going through layers of the same spin. Whereas if the thing that's being sensed switches the orientation of the ferromagnetism in the sensor, so it's opposite to the reference, we have a high resistivity. The spins, the electrons which are carrying the spins, they get scattered a lot. And so in order to sense the orientation of a field with this sensor layer, of course, the reference layer has to not switch too, right? If they both switch, they'd always be parallel, and we wouldn't have any mechanism for the sensing. And the thing that stops it switching is the antiferromagnet. And so here's a cartoon of how that works. It's called exchange bias coupling. The ferromagnet is kind of pinned in its orientation by the antiferromagnet. So every magnetoresistive sensor, of which there are, I don't know how many, maybe not as many as ants, but very, very many magnetoresistive sensors in the world, it wouldn't work without an antiferromagnet. So antiferromagnets are now also of massive technological importance. So really, I mean, the fundamental research that we're doing today is, of course, going to enable these kinds of technologies in decades from now in the same way that the fundamental research on antiferromagnets is enabling us to have magnetic sensors today. So tell your Congress people that, please. Okay, so a few other kinds of hidden order that I want to just quickly mention. I just picked a few kind of favorites. Let me start with the, let me go back a picture to this picture of the cuprates and show you, just point out one of these other phases, the pseudo-gap phase, which also has a kind of weird, kind of hidden order, we think. Maybe it's a phase transition into it, maybe not. This is a kind of a dashed line. Maybe it's kind of a crossover. And one of the leading models or leading pictures of what this hidden order is from our visiting colleague Chandra Varma, who's here in the audience here, which is that there are hidden orbital currents that are breaking time reversal and space inversion symmetry. And these are consistent with all of the measurements on the pseudo-gap phase. I think maybe you'd agree, Chandra, that there's no really a direct measurement yet. This would be really a nice thing to have, oh, okay, we can discuss this afterwards. Maybe. I don't want to get myself into trouble. I still think they're kind of hidden. Well, some of the actinide materials, where there's very, very strong spin-orbit coupling and complicated multiplets of the electrons, have orders that are very difficult to measure directly. And this was an interesting one. There was a divergence in the specific heat, but no apparent change in the structure. And it was found, again, by neutron scattering, that it has an antiferro charge quadrupolar order. So I've tried to draw the quadrupoles. These are the kind of charge quadrupoles on the uranium atoms. Subsequently, this was also found to have a structural distortion. Of course, if the charge of the electrons order, the structure has to change too, but it was so tiny it could not be detected at first. And then this is one of my personal favorites, lead telluride. It's a very good thermoelectric. So it will conduct charge, but it scatters a lot the phonons, the lattice vibrations. And this was not understood until it was identified that there are polar nanodomains. So if you look at the lead atom here, you see that the electrons in red are separated from the lead ion. So there's these little dipoles in the crystal structure. These are correlated, but they're not, they don't completely lower the symmetry to a new phase. But these are believed, this kind of hidden correlated order is believed to be responsible for the good thermoelectric behavior of lead telluride. And then I put this one in because I thought this could flush out if there are any astroparticle physicists in the audience, because you might object. Is anybody working on dark matter? Okay, very good. So maybe you could see it flushed you out. I'm not sure if it's okay to think of dark matter as a hidden order. It's for sure hidden, right? And if it's formed by a symmetry-lowering phase transition, is that an order? But perhaps one could also think of dark matter as a hidden order. Okay, so there's some examples. Any questions so far, particularly from the students? Clear? Any objections from the dark matter people? No? So, okay, so are there other kinds of magnetic order still hidden? And probably, right? Otherwise I wouldn't have scheduled or promised to keep you here for 45 minutes. And if so, where should we look for them? And if you start from the thought that probably kind of anything simple has been found already, then a place to look is a composite order, right? Maybe we can find an order where, one property is 0 and another property is 0, but some kind of composite of those two properties is non-zero, right? Then it might be difficult to measure. Maybe we have a tool to measure A and a tool to measure B, but they're both 0. And so this composite then might be a good place to look for hidden orders. And the example that I'm going to focus on today is what Jeff mentioned in the introduction, some combination of magnetic order, which I'm going to keep calling mu, and ferroelectric order, which I'll call R, the electric dipole, just position R. And so in a ferromagnetic material, I have a spontaneous magnetization that I can switch with an external field. My magnetization is non-zero, and there's nothing hidden about that, right? I can pick it up with a magnet. It's a great big non-hidden kind of order. In a ferroelectric material, I have an electric dipole that I can switch with an electric field. The expectation of value of the electric dipole operator, the position operator, is non-zero. And again, nothing hidden. And of course, both of these orders are very interesting. Jeff mentioned that he and I have both been interested for many years in these multiferroic materials that are simultaneously ferromagnetic and ferroelectric. And these are very interesting. They let you, for example, control the magnetism with an electric field. But I'm not going to, actually, if you want to hear about those, you had to come last week to the materials department colloquium. So you missed it. But what I want to think about today instead is materials where there's no net magnetization. So there's no ferromagnetism. There's no net electric dipole. There's no ferroelectricity. But this composite, this product of magnetic order and electric order is non-zero. And this is going to be kind of hidden, right? I can't just take a magnet and pick it up or look for its electric stray fields. We're going to look for this kind of order. Okay. So what could where would I expect to see such a mu times R order? So this hedgehog is representing a magnetization density. It could be maybe around an atom in a material, or it could be like in the unit cell of a material. It could be in some metamaterial. And the arrows are the orientation of the magnetization. So I can see I have no magnetic dipole here, right? The net magnetic moment of this hedgehog is 0. But if I go, say, along positive x, then my arrows are pointing to the right, so mu dot r is positive. If I go along negative x, my arrows are pointing to the left, and my x is negative, so mu dot r is positive. So this hedgehog has a non-zero kind of composite order. It's magnetic times electric dipole kind of composite is non-zero. So if I have a material or a system where I have such magnetic textures, then I can have this hidden kind of composite mu and r order. You can imagine other scenarios. If I have a swirl of magnetization, then you can go through the same exercise if you get bored and convince yourself that in this case mu cross r is 0, or such a kind of quadrupole. Again, the product of the magnetization times the electric dipole times the position is non-zero. And in condensed matter, we call these kind of spin textures often magnetoelectric multipoles. It'll become obvious in about 5 or 10 minutes why we call them that. I think in dark matter, if I understand correctly, such a texture would be an axion. It's coupling to E times H. And in nuclear physics, the anapole moment is described. It has such a texture, but I'm outside of my expertise in making both of those statements. So it's not only in condensed matter that we're interested in such magnetization textures. Okay, so now I get to the outline of my talk. That was the introduction. So what are these magnetoelectric multipoles, and when do they show up in materials? And then the most important thing, I think, is what properties do the magnetoelectric multipoles cause? And this is how I came at this kind of hidden order business. I was trying to design for particular properties, and I thought, okay, this is kind of maybe a helpful way to think about how to look for materials that have these properties. And then, can we directly measure them? So I'd say at the moment, no. And so I'm really hoping from all the experimentalists in the audience to get some new ideas about, we have many attempts to measure them that are not inconsistent with their existence, but none of them are really, proof yet. Okay, questions? Anybody? There's a boring derivation coming, so you might want to ask questions now. No? Okay. Okay, this is a 4-slide boring derivation. So hang in there, or do something else for 4 slides if you get bored. So this is, for those of you who are you taking electricity and magnetism this semester, first-year graduate students, or not? Last semester. Okay, so then you know all of this. I can be very quick. This is, I think, on the page 1 of Jackson. How does a magnetic material interact with a magnetic field? Of course, you know it's the dot product of the magnetization density times the magnetic field. And here I have some general magnetic field and some general magnetization density, and I integrate that over all space. Okay, so that's page 1 of Jackson. Usually, though, we don't bother with this, taking care of this whole integral. We write this as the integral of some general magnetization density times some uniform field. And then that just reduces to the magnetic dipole moment times the field. So the magnetic dipole moment is the integral of the magnetization density over the whole space. And for most of what or often in magnetism and magnetic devices, this is enough. We don't have to go beyond this level of description. But of course, it's an approximation. We've assumed that the field is uniform, at least on the length scale that we're interested in. And if we want to improve this approximation, one way that we can do it is make a multipole expansion for this interaction energy of the magnetization density in powers of the field gradient. And so here's the first term again in the multipole expansion, the usual dipolar Zeeman term. And the next term, this is the one that I'll be talking about most, has in it an R times a mu of R times the derivative of the field with respect to R. And so immediately you can see, here's a nice way to think about these magnetoelectric multipoles. They're the first order correction to thinking of my general magnetization density as just dipoles. Okay, they tell me about any non-sphericalness of my magnetization distribution around my atoms, for example. Okay, so this, do I have this coming? Oh, yeah, so I just wrote the same thing again. So here's my next term in my multipole expansion. Now here I had an integral over mu of R, that was my dipole. Now I have an integral of R in one direction, mu in another direction over space. And this is a 9-component tensor, which we call the magnetoelectric multipole tensor. And so if you like 9-component tensors, you can stop there. I find it more, that's the end of the boring derivation. I find it more convenient, rather than carrying around in my HID a 9-component tensor, to just decompose this into its irreducible parts. And then I get my hedgehog, which is the R dot mu of R. It's a scalar. I get a 3-component vector, the R cross mu of R, which is called the magnetoelectric toroidal moment. And this can be around X, Y, or Z. That's why it's 3 components. And then the remaining 5 components are the traceless terms in the tensor, and these are my magnetic quadrupoles. And so whenever I have such magnetization textures in my system, in my material, then I will have what we call magnetoelectric monopole moments or magnetoelectric hedgehogs, magnetoelectric toroidal moments, or magnetoelectric quadrupole moments. Okay. And for me, at least, I can't remember if Jeff said, I trained as a chemist, and so I'm used to thinking of like atoms and charge densities around atoms and atomic orbitals and molecular orbitals. Having these kind of spherical harmonic pictures is much more intuitive about thinking where do the electrons go? Where do the electron spins or the electron orbital moments go? Okay. So these are the quantities I'm going to be talking about. Questions? Yes, please, Taylor.
Yeah, mind going one step back?
Of course.
So when we're discussing this expansion, sort of the simplified description for the moment magnetic field interaction, it seems like that first term we had discussed involved the derivative with respect to the magnetic field.
Yeah.
In terms of coupling to a lot of these terms.
Yeah.
Should I think of that as like the Weiss field, or is it the actual internal field?
So you should think of it as, so if I were to look at the term in the free energy that couples to this thing, it would be the divergence of H. So there'd be a term in the free energy minus A times the divergence of H. So H is just the external field, right? And here, this one would couple to, it would be minus T times the curl of H. And this, sorry, go ahead.
Apologies. The moments we're discussing here in expansion, are they at the atomic scale, or are they much more like nano or mesoscale?
So both. I mean, in the same way that in just a ferromagnet, when you think of only the dipoles, I have a magnetic moment on each atom, right, if I have a local moment ferromagnet. And I also have a macroscopic thermodynamic magnetization. So both. And I'll come back and actually look at some of those. So, yeah, good questions. Anybody else? You're not a first-year student. So, no. Yes, please. This is the quadrupole. So for example, the z-squared quadrupole would be rz mu z plus rz mu z minus the trace, basically. No, it's five component. It's basically the d orbitals, right? It's the spherical harmonics that give you the d orbitals. The L is equal to 2 spherical harmonics. Yeah. Okay. Anybody else? All right. So let's look at the properties, because again, this is that was the kind of the precursor. I think for me, the properties are of course the interesting part. And you could maybe you argue that if we have these properties, then we do have a direct measurement. I'm not sure, but so two properties I want to mention. One is the linear magnetoelectric effect, and the other is surface magnetism. So any material that has these magnetoelectric multipoles that are ordered ferroically, so we have a net magnetoelectric multipole, has both of these properties. It has a linear magnetoelectric effect, and it has a bulk boundary correspondence that gives you an intrinsic surface magnetism. Okay. And I'm going to take for an example for you, my favorite linear magnetoelectric, chromium-203, to illustrate these concepts. So here's the crystal structure of chromium-203. The chromiums are in blue, and the little arrows are the magnetic moments. It's largely a spin magnetic moment. And the oxygens are in red. And if I just look at the dipoles, I would say, okay, chromium-203 is an antiferromagnet, and I'd be done. That would be all that I would think would be interesting about chromium-203. But chromium-203 is actually has ordered magnetoelectric multipoles, and I'm going to make two kind of cartoons to show you why. So the first one is if I just look at these pair of magnetic moments here, there are two magnetic moments pointing out. I could rewrite that as like a hedgehog pointing in and a quadrupole, right? If I add these together, I can see I end up back to where I started. And then down at the bottom, I have the same thing. So just from this simple thought experiment, I might imagine that I have a bulk magnetoelectric monopole, a hedgehog, plus a bulk z-squared quadrupole in chromium-203. And this would be, back to the question, this would be really in the unit cell. This is like a macroscopic thermodynamic quantity. The other thing, if I look closely, you see that my upspin chromium atom is shifted from the center of its oxygen octahedron in an up direction, right? It's not in the middle. So it has a local R, if you like. It has a local electric dipole. And the downspin chromium is shifted from its octahedron in the down direction. So it has a local electric dipole in the opposite direction. But mu times R, both up or both down, is conserved. Okay. So I'm expecting just from the simple, I haven't done any complicated group theory, just from thinking that I might have this property here. I'm expecting a magnetoelectric monopole and a z-squared quadrupole. And we know how to calculate these things. So I'm an electronic structure theorist. I do very simple density functional theory calculations. When I do that, I have access to the full electron density, the charge density, and the spin density, the magnetization density. And so I can look around my atoms, and I can calculate R times mu of R in a sphere around each atom. And when we do that, we find indeed we have hedgehogs around each atom, and we have these z-squared quadrupoles. And so what this is telling us is around the atom, it's not a perfect sphere of magnetization density. If it were, I'd just have a dipole. But I have these higher order multipoles that correspond to the asphericity. We also know how to calculate, it's a bit more complicated. We know how to calculate these quantities integrated over the unit cell. This was actually a whole PhD thesis of Florian Törle. For those of you who work on ferroelectrics, we have all the same problems as in the modern theory of polarization for ferroelectrics, but we know how to do it. And when we do that, we find that indeed we have a Z component of this tensor and in-plane components that are non-zero And the in-plane components are different from the Z component. So we know what magnetoelectric multipoles we have in chromium-203. Okay, so it's chromium-203, I wouldn't say is a antiferromagnet. I would prefer to call it a ferromagnetoelectric. It has a net magnetoelectric multipolization. It has a ferroically ordered quantity. It's a ferroic. And this tells us a lot more about the properties than thinking of it as an antiferromagnet. Okay. So whenever I have a material with such a net magnetoelectric multipolization, then by symmetry, I have a linear magnetoelectric effect, which means if I apply in a magnetic field, I induce an electric polarization, or if I apply an electric field, I induce a magnetization. And the induced quantity is linear in the applied field. Okay. So this is quite unusual, maybe even a little bit remarkable, right? Normally with an electric field, we modify the electric properties. With a magnetic field, we modify the magnetic properties. Here we have this like kind of cross-coupling, the conjugate of the kind of the field. It's not the usual conjugate field for the property. And I thought, rather than kind of work through the symmetry here, I'd just give you a cartoon of how this works. Any questions before I go on, by the way? So, happy with what the linear magnetoelectric effect is. I'm applying an electric field and inducing a magnetization. So here's a cartoon. It's just some little, maybe transition metal oxide. Here's my transition metal, oxygen transition metal. I'm not sure if in your electromagnetism class or if you've learned the good enough Kanamori rules. Do you know about these? I know in chemistry we learn them quite early on, but all you have to know is when I have a transition metal, oxygen transition metal bond angle that's 180 degrees, the interaction between the spins on the transition metal is antiferromagnetic. They want to point anti-parallel. But when it's 90 degrees, this interaction is ferromagnetic. So here I've got 180 degree, almost 180 degree transition metal, oxygen transition metal. These want to be antiferromagnetic. I've put them in a triangle so they can't all be antiferromagnetic to each other, just geometrically. And so they go to be 120 degrees. So here's my material. This is its ground state. And maybe this unit cell is repeated over and over again. And this has no magnetization, right? Everything, it's like a hedge, it's a hedgehog. That was I want to make the point. Here I have my magnetoelectric monopole, no magnetization. So let's look at what happens when we apply an electric field. So I apply an electric field. The positive cations shift along the field, and the negative anions shift opposite to the field. And so now this angle is very close to 90 degrees, and this one's even more close to 180. So these magnetic moments, if we go back to my rules, want to be ferromagnetic, and so they rotate and allow these magnetic moments to be even more antiferromagnetic. And so I end up with my electric field inducing a magnetization. So I have this diagonal magnetoelectric response as a result of the magnetoelectric multipole. If you get bored, anyone who gets bored, you can work out for this starting arrangement what your magnetoelectric response will be. I just should have brought a prize. We'll have a quiz at the end. So, and you'll find there's also a magnetoelectric response, but it's in a different direction. So, okay. Here's the data. So this effect was predicted in chromium-203 in 1959 by Igor Jalashinsky and measured a year later by Astrov. He didn't label his axes. This is the magnetoelectric response in some units that he didn't state. So this is the temperature. Oh, he has labeled this one. Here's the temperature hidden in here. This is the magnetoelectric response as a function of temperature parallel to the axis of the chromium-203, and here it's perpendicular. And so you see that they're different and they're non-zero, and these are the non-zero components. The other nice thing is one can use this, it's the same physics as the linear magnetoelectric effect. One can use this to select for a particular antiferromagnetic domain. So if I apply my electric and magnetic fields parallel to each other, I pick out one sign of the hedgehogs. And if I apply them anti-parallel, I pick out the opposite sign of the hedgehogs, because the two domains have the opposite magnetoelectric response. And so this has been done. It's very difficult to get the signs right in this. It's a bit complicated, but particularly because the neutron diffraction, I don't know if there are any neutron people here. You guys use magnetic moment and magnetic spin interchangeably, which is very confusing. But anyway, we think we even understand the sign. But importantly, we get opposite signs of the hedgehog, which correspond to the opposite antiferromagnetic domains. And in general, if you just have a general antiferromagnet, it's not so easy to pick a particular domain, right? It's not that there's not kind of a conjugate field, a generic conjugate field for an antiferromagnet, but there is for a ferromagnetoelectric, and it's a composite field of E and H. Okay. Questions? How are you doing for stamina? Can you handle to hear about surface magnetism? Yeah, this one is a good one because for some of you, it's one of your friends who did this work. I'll show a picture of her in a moment. Yes, please. Yes, of course.
You showed the hedgehog. Is that magnetic field, those arrows?
It's magnetization density. So it's if you like to think in terms of spin, it could be spin or orbital, it doesn't matter. But it's the density. So normally we think of the spin density as just an arrow. If you like, you've got an arrow and then this kind of little hedgehog superimposed on it. So maybe you could think of it that instead of just a magnetic dipole, so this would be my magnetic dipole. If I had a perfectly spherical magnetization density around my atom, I have a bit extra up here and a bit less down here. And a bit less down here because the hedgehog is added to the dipole. So it's like an aspherical magnetization density. Does that help? If I want, and again, the term in the free energy that would couple to this hedgehog is minus A times the divergence of H. If I could, around the atom, apply a diverging magnetic field, I'd favor one hedgehog over the other. That's not easy to do. It's better to do it with E and H, right, than a local atomic scale diverging H. So H diverges, and M is hedgehog-shaped, but B does not. Yeah, very good point. So it's not a magnetic monopole. We call it magnetoelectric monopole, and I think that's a bit confusing. It's better to call it a hedgehog. So no, because don't you think? Because monopole implies like that we've discovered like some fundamental, like really exciting thing. It's a hedgehog, and you see. I mean, you can see it if we go. Can I go back? Yeah, here, right? This is not. There's nothing. We have such a kind of arrangement of magnetization density. There's nothing untoward, there's no fundamental Dirac hidden funny thingy in this. It's just my magnetic moments are all pointing out. So it's like it's a hedgehog. But absolutely right. If I had a diverging B, then we should be really excited, right? But no, don't have one of those. Other questions? Okay, quickly, surface magnetism. Let me just give you a quick argument about why when I have a magnetoelectric multipolarization, I should have a surface magnetism. And I want to go back to Jackson. I have a ferroelectric polarization, then you have a surface charge, right? And the size of the surface charge is equal to the size of the polarization. My surface polarization, it's E times R over volume. It's measured in microcoulombs per square centimeter. And the amount of charge in microcoulombs per square centimeter on the surface is equal to the size of the ferroelectric polarization. So notice, if I want to charge rho on the surface, the bulk quantity that I have to have is the thing that's rho times R, the electric dipole. Here I'm saying I want to have a magnetic dipole on the surface. I want a surface magnetization, and that I get from the quantity that's mu times R, and that's my magnetoelectric multipolarization. So there's a simple hand-waving argument. One can be, of course, a bit more rigorous. This was my COVID lockdown project. I actually wrote a paper on my own that had science content in it, which when you get to be our age, it's not so often that one gets to do that. So here in chromium-203, for example, I have this MZZ component will give me a surface magnetic dipole equal to the size of the bulk magnetoelectric multipolarization. So that one can assert, and Sophie Weber, who I think many of you know because she was a PhD student in the group of Jeff, actually came to my group and calculated this, and we started off with the stable 001 surface of chromium-203. Sophie showed with spin dynamics that we had to cut off the top spins because they don't order or they disorder at higher temperature than the bulk. And then she calculated the MZZ associated with this surface. She got a number. This was a number from density functional theory from a calculation. And this was measured and using NV magnetometry, which I don't know, is anyone here doing NV magnetometry? it's a very difficult measurement to interpret. So one measures a field. One has a little magnetic sensor in a tip from a nitrogen vacancy in diamond. One measures a field, and then one has to extract from that field what was the surface magnetization that caused it. But the range of values spanned by the uncertainty in these measurements include minus 2.4 Bohr magnetrons per square nanometer, and they have the correct sign. So this is this we were very excited about. Whoops, sorry. But you might say, well, isn't that obvious, right? This is my surface. I can see that I have a net magnetic moment at the surface, right? Because I just can look at the dipoles, and they don't cancel. They cancel out. These guys are higher up. The purple guys are higher up than the blue guys. So of course I have a net magnetization. But what gets really interesting is when one looks at the surfaces, that if you just look at the dipoles, they're magnetically compensated. If I just look at the dipoles here, I'd say, there's no net magnetization here. But there is. And because we know that because there's a component of this magnetoelectric multipole tensor pointing in this direction. And I can see that if I superimpose my hedgehogs on top of the dipoles, I see that it's not magnetically compensated. There's a net surface magnetization. It's only when I naively think of my antiferromagnet as it's only magnetism coming from the dipoles that I think it's compensated. It's actually not in this case, and it's not because of the hedgehogs. And this I was super excited about because this is something that's annoyed me for decades, actually, since I was a PhD student, is that many of these surfaces that appear to be magnetically compensated, they have this property of exchange bias coupling that we talked about right at the start of an important application of antiferromagnets. And if we just look at the cartoon that I showed you, we'd not expect that, right? Here it looks like the exchange bias coupling is coming from the uncompensated spins at the surface. And so now we understand why these apparently compensated magnetic surfaces are showing exchange bias coupling. So that we were very excited about. Okay. Can we directly measure them? I'll stop. I'm going to stop after this slide. So we've been not successful, and I don't want to give the impression to the students that research that one is successful in research generally. Most of the time, one's not, I'd say. And the things you fail at are actually perhaps the most exciting because then you learn something. So here I'm just on one slide summarizing some of the attempts we've made to really directly measure. I mean, one could say we're measuring the response. We know these multipoles must be in there by symmetry and by the fact our materials have these responses, but we'd like to really see them like directly. So we've tried with spin polarized spherical neutron polarimetry, where they should appear as a very small correction on the magnetic Bragg peaks. And the data are not inconsistent with that correction being there, but the correction is not out of the noise yet, so we need higher power neutron sources, or we need to be more clever and come up with materials where the difference would be easier to measure. We tried Compton scattering. So these antiferromagnets, because they break time reversal symmetry, whereas a normal antiferromagnet would not, should then have a magnetic Compton scattering signal. And again, our data are not inconsistent, but the response is not out of the noise. And we've tried with muon spin resonance spectroscopy by where we put a charge on the top of a magnetoelectric, and then this creates an image monopole and gives a divergent B field in this case, but only outside of the surface. So it's not really divergent because it never gets to the monopole. So we've tried to measure this diverging field, and again, the data are not inconsistent, but I'd say not out of the noise. Okay, I'm going to stop there, and then maybe if people are done and we want to ask questions about this, we can. And if people are super interested, I can talk about the next order terms, the octopoles, which have a mu or 1 or 2, but we'll maybe stop and take questions first, and then the enthusiasts can stay. These are the ones that cause altomagnetism. So those of you who are interested in altomagnets, you have to look at magnetic octopoles or magnetic triaconta dipoles, but maybe some of you would rather go and have a beer instead. So let me stop. It's hard. I mean, magnetic triaconta dipoles or a beer. That's a tough one. So, okay, I think I've shown you that in non-centrosymmetric, non-time reversal symmetric antiferromagnets, we have these magnetoelectric multipoles that form this kind of hidden multiferroic order. They're not multiferroic, but they break time reversal and they break space inversion. These magnetoelectric multipoles give you a linear magnetoelectric response, and they give you an intrinsic surface magnetization, even if it looks like there shouldn't be one if you just look at the dipoles. We've pretty much failed to measure them. Well, NV magnetometry, I think, measures their effect, their surface magnetism. We've tried these other techniques. I was super excited in the condensed matter seminar today to hear about these orbital angular momentum beams, because somehow I think there has to be some correspondence there that we can exploit, but I don't know what it is yet. And this I didn't talk about, but I was always down on centrosymmetric materials because if you like ferroelectrics, they're kind of not very interesting. But I've changed my mind. So if you have a centrosymmetric antiferromagnet that's breaking time reversal symmetry, then you can have ferroic magnetic octopoles or even magneto-triaconta dipoles. And this can also give you a lot of interesting physics that, again, wouldn't be there in a kind of conventional antiferromagnet. So I'll stop there. I'm happy to answer any more questions. And again, to remind you, I'm sitting in the 4th floor of Burge, and I have time. I'm on sabbatical, so all I want to do is discuss science with people. So please stop by and tell me about what you're doing. And I have to thank some government agencies and private foundations for supporting our work. And thanks a lot for your attention.
Magnetoelectricity that allegedly arises in a topological material in which you are topological insulator, and yet you have antiferromagnets that create
So I have to give you a disclaimer that I'm not the expert person to talk about topology, but maybe Jeff can correct me. But the Chern-Simons term in an axion insulator, symmetry-wise, is the same as the magnetoelectric hedgehog. So it has this diagonal magnetoelectric response. The size, and so people have tried, for example, this experiment that I showed to try to measure the hedgehog structure in chromium-203. This has also been tried, this one down here, for a topological insulator, where one has to, if you take a topological insulator here, in principle you have the same, you can do the same experiment. The difficulty is you somehow have to break the time reversal in the topological insulator. And I guess now with some of these magnetic crystalline topological, is Joel here? He's not, is he? He would be the person to explain the difference. Yeah, so I don't know if that answers your question, but that's the extent of my knowledge about the question also. So we should maybe discuss with Joel afterwards or another time.
Let's see, maybe you can go up here and come back. Go ahead.
Thanks for the talk. So when you mentioned many times mu.
Yeah, magnetization, yeah.
Usually we think that is coming from the spin.
Mm-hmm.
It should have orbital orbit.
Yeah.
You know, any interesting, I'm assuming that all that because explain how to spin orbit. Is there any orbital quantifier or something?
Yeah. So I'd say that everything I said in terms of the symmetries doesn't matter if it's spin or orbital. In the chromium-203, the orbital contribution is really small. It's mostly spin. It's D3 octahedral symmetry, so it's mostly spin. But for sure, if one has strong spin-orbit coupling, my goal would be to find a material where one has a kind of static order in one of these higher order multipoles with no dipolar order. And that would the only way I can think to do that is with strong spin-orbit coupling, because then you can end up with a case where you have a very magnetic thing, but its net dipole can come out to be 0 because of the spin-orbit multiplet. And so there's some very interesting physics. I haven't found such a material. In principle, 5D1 with very strong spin-orbit coupling, if in the purely ionic atomic limit, should have such behavior. The dipole is 0, and the higher order multipoles are not. So, so yes is the answer. Even the local dipoles, though, even the local dipoles would be 0. So, I mean, also, I'm completely with you if you think, well, I just simply don't care about this as an antiferromagnet. I'm just going to look at my dipoles. I mean, that's absolutely a valid point of view. I mean, I don't agree, but I respect your point of view. But wouldn't it be nice to have something that didn't have dipoles, right? Where then nobody could say that it's just antiferromagnetic dipoles. In principle, one can have that. And this would, I think, have to come from very strong spin orbit effects. Yeah. It's a very good question. So I think there's I'm not sure who's next. So Jeff, you're in charge.
Yeah, I think.
Yeah.
Go ahead.
You mentioned that some of the scattering breaks time reversal symmetry. What exactly does that mean? Does it mean if you run the collision?
Oh, sorry, I was maybe a bit unclear. So the antiferromagnet, the material, breaks time reversal symmetry. So if you have a ferromagnet, and if you just think of say an orbiting electron giving you a net magnetic moment, if you reverse time, then you get the opposite ferromagnet. And so we say that breaks time reversal symmetry. Most antiferromagnets, or conventional antiferromagnets, don't do that. Of course, if we have dipoles and we reverse them, it gets reversed. But in many materials, we can then do a translation of the lattice and we get back to where we started. So we say that those don't break time reversal symmetry. These ones do. So if I reverse all my dipoles, there's not a way I can just translate my lattice and get back to where I started. So when we say, in condensed matter, when we say reversing time, we basically mean flipping all the magnetic dipoles. Yeah. Sorry, I should have explained that. Yeah.
So maybe we'll go up here. Excellent talk. You addressed the material as an antiferromagnet. You were distinguishing between different mechanisms that you can get antiferromagnetism.
Mm-hmm.
For example, in the case of a spin valve, the ring head of the hard disk drive. So the AFM material is a kind of a synthetic antiferromagnet.
Mm-hmm.
Individual material that has that direct exchange antiferromagnetism.
Yeah.
The details of the process changes any of these interesting things that you explained today?
So actually one thing I think I perhaps should have emphasized more is, for example, the linear magnetoelectric effect can only occur in insulators, because otherwise if I apply an electric field, I just conduct. But this kind of like more macroscopic layering, for example, like you have in the spin valve, there's some beautiful work recently from groups that have taken really 2D materials that have, say, a net dipole. They'd be like the spin of the antiferromagnet, and then layering them in different ways. Is Veronica here? What is the material? Yeah, manganese bismuth telluride, and they're playing with heterostructures and constructing, and it depends on the number of layers then whether you get overall a ferromagnet or a hedgehog, which is really beautiful, I think. Yeah. So, in synthetic, so my colleague Laura Heidemann, who makes these metamaterials, has been trying to make toroidal moments with micron-sized bars for the components, and I say the jury's still out, but in principle, but because the symmetry is the same, right? The scale, of course, the size of the response could be quite different, but yeah, for sure, that's a good question.
Maybe the last one. Thanks for the talk. I'm wondering, maybe on a bigger picture,
Mm-hmm.
start with that hidden orders, their orders which have to be direct spin method.
Yeah.
Is it possible to have a hidden order where it could never be measured? Like you could prove it, like it's not something that is observable, but it's still there's something that is not observable, but it's still ordering.
No, I would think if you have any order, if you have the right probe, it's got to couple to some probe, right? It might be a probe that we don't have. I don't know. This is a philosophical question. Any Any other thoughts from the audience? Like an absolutely undetectable ever hidden order. Dark matter people want to want to kick in on that one? I don't. No, I'd say if anything, there's got to be some probe. If you get some kind of order, there's got to be a probe that couples to it. You just may not, you may not have the energy scale you need or the symmetry. You may not know what the probe is. But I would say that's my bet. But you can come back to me.
I'm philosophically opposed to such order, but
Thank you. Thank you, Jeff. I'm with you on that one.
at this point,
That's a good point to stop. Yeah, let people go for a beer.
and